And so we're going to be talking about efficiency and sorting and searching. Basically, what my goal is, and what you're going to be doing on the homework, is we're going to be looking at 7 algorithms, and you're going to be experts on those 7 algorithms. You're going to be able to draw out pictures tracing the algorithms. You're going to understand the code that implements the algorithms, and you're going to be able to tell me what the big O is for each of these algorithms, and we'll be talking about big O a little bit too. Getting an Excel spreadsheet set up here. Okay, so I'm just going to start off by listing the algorithms we're going to be looking at. We're going to look at linear search, which you probably are all familiar with, binary search, which you may be familiar with. I don't think, if you took all the classes from me, I don't think we ever covered that. But and then selection, bubble, sort, insertion, sort, merge. All right, so that's the goal. Let's begin by just talking briefly about linear search. That basically just means, here's my array. Actually, let me put some.
Dave, was this the assignment you were warning about a couple weeks ago?
No, the assignment that I was warning about a couple of weeks ago is the one that is due next Monday, the assignment 8.
So okay, roger that.
The linked lists with the memory problems, right?
Gotcha.
Yeah, so this is actually, in this assignment, I'm actually not going to have you do any coding. You're just going to be drawing me pictures of exactly what it is I'm going to be doing today during lecture. And to show me that you understand how these different algorithms work, okay? So the way linear search works is you just start at the first element of the array, and you compare each element of the array with the target, and you keep going until you find the target or you reach the end of the array, right? So what I'm going to ask you on the homework and potentially on an exam would be list all of the numbers that are going to be examined by the linear search algorithm if this is the array and say the target is 15, right? So you would say, oh, it's going to look at the 82, and you'd make a list. It's going to look at the 82, it's going to look at the 55, it's going to look at the 92, it's going to look at the 67, it's going to look at the 90, it's going to look at the 38, and then it's going to look at the 15. And then it'll be done. Okay? That probably seems a little silly. I wouldn't even have you do that, except it's just a sort of a basis of comparison with how binary search is going to work, and, just to show me at least that you know what a linear search is. So I'm not even going to do code for this because I'm pretty sure you could all come up with code that goes out. let's talk about big O for a minute. So big O, so there's 7 of you right now. I'm just curious. Show of hands in the participants window. How many of you have heard of big O? We got 1 no. Okay. Okay, just curious. So, I got another no. Big O is just a technique that computer scientists use to indicate in very broad terms the efficiency of an algorithm. And when we're talking about big O, we're not talking about, oh, does this run in, a tenth of a second, or does it run in 2/10 of a second, right? Well, when we're talking about big O, we're talking about like major differences in the efficiency of an algorithm. And the way that we express that basically comes down to what family of functions does the algorithm fall into? Is it a linear algorithm, which would mean that the number of operations depends on the number of elements in the array? Or is it a n squared algorithm, meaning that the number of operations is going to depend on the square of the number of elements in the array? Or is it exponential? Is it 2 to the n? Or is it constant? Like if I said, what's the big O analysis of finding the element at index 7 in this array, that would be a constant function, right? It doesn't depend on the size of the array at all. So anyway, we'll be talking a lot more about that. But let's analyze linear search and talk about big O. So on average, when I'm looking for something in this array, how many, I'm going to say, comparisons am I going to have to do? So if I'm looking for the 60, how many comparisons am I going to end up doing? Right, so the bottom line is, however, well, I guess if you want to be more precise, well, I could say on average, it would be n over 2, right? But it turns out that, as I was saying before, we don't really care about the over 2, right? Whether it's n or n over 2, it's still a linear function. So the way we write that is we say big O n. And I hope everyone's clear on why I'm calling that linear. It's similar to like if I had a function f of n equals n, we would call that a linear function, right? Just if we were in an algebra class and your algebra teacher said, asked you what kind of function that was, you would say that's a linear function, right? So later on, if we get to something that's big O of n squared, we would call that a quadratic algorithm, right? Because if we were in a math class and you saw f of n equals n squared, you'd say, oh, that's a quadratic function, right? So hopefully that's not too difficult in terms of the math behind it. If it is, you may need to do a little just review of different types of functions: quadratic, linear, exponential, and we'll talk about some more as we go. Okay, any questions about linear search? All right. Binary search. So the idea behind binary search, first of all, binary search only works when the array is sorted. So I'm going to get a sorted version here. I guess I should label this. The theory behind binary search is, think about if we are going to use a paper telephone book. I don't know if you guys even know what a telephone book looks like anymore. And I don't have another good example, but you can probably guess. Okay, just a whole book full of phone numbers listed alphabetically by name, right? If we're going to look for a name in that phone book, we're not gonna like look at the first name in the phone book and say, oh no, that's not it. Then look at the second
That'd
name
be
in the
linear
phone book.
search, right?
That would be a linear search, right?
Yeah.
So what we're going to do is probably we're going to, as humans, we would probably make some sort of a guess about where in the phone book it might be based on what the last name starts with, and we would open the book there, right? And then if it was, if the name we're looking for comes before that page in the phone book, then we will forget about this last half of the phone book, and we'll look for that name just in the first half of the phone book, right? So that's basically what we're going to do with binary search, except that we're going to simplify it quite a bit. We're going to just always look at the middle item in the list and decide whether our target is before the middle item or after the middle item. And then we're going to narrow down the part of the array that we're looking in like that.
Does a binary, I would assume you'd have to sort first before you binary
Yes.
search anything, though,
In order
correct?
for a binary
Okay.
search to work, the array has to already be sorted. Yes.
Okay, just making sure. Cool.
Okay, so we're going to have a variable called low and a variable called high to keep track of the range of values in the array that we are still considering, right? So in our example, when we start, low is going to be 0 and high is going to be 11. And then we're always going to look at the middle item within that range, okay? So, and the middle item turns out to be low plus high divided by 2. And we're using integer division, so that's always going to result in an integer. Okay. So in this, let's say that the target is 90. Okay. So let's go through this process. Low plus high divided by 2 is what?
5.5.
Well, except these are integers. So 11 divided by 2 is 5, right? Everyone okay with that?
Yes.
Okay. So we're going to be looking at, oh, I forgot to put my indices here. We're going to be looking at element 5, which is 55. And we're going to say, okay, target is greater than 55. So we're going to change the value of low so that instead of looking between 0 and 11, we're going to be looking between what and 11? Well, we know it's not anywhere down here, right? And we know it's not the 55. So we're going to set low to 6. Okay? Everyone understand why 6? No questions about that? Okay. All right, so that's our first time through the loop. So we're back to the start of the loop again. We're going to say, okay, low plus high is 17. 17 divided by 2 is 8. So now mid is 8. And so we're looking at element 8. And we see that target is greater than that number. So we're going to bump low up to mid plus 1, right, which is 9. Tracking with me? Everyone good? Anyone need me to do it again? Okay. I see someone still has a no. Okay, they got things changed. Good. All right. I actually appreciate if you answer if you use the yes and no buttons when I ask you a question like that. It's actually kind of nice. I'm getting a little feedback. Okay. So let's see. We're gonna. Oh, actually, okay. I forgot one thing. I want to write down what the numbers are that we look at, because that's how you're going to prove to me that you understand binary search. You're going to actually list the elements that are examined by the algorithm. So the first one we looked at was the 55, and then we just looked at 82. And then now we're back at the top of the loop. Low plus high divided by 2 is 10. So now we're looking at the 92, and we notice that target is less than 92. So now what we do is we set high equal to mid minus 1. And that was the 92 that we just looked at. Okay. All right, back to the top of the loop. Low plus high divided by 2 is 9. So now the number we're looking at is 90. So we found what we were looking for, and the last number we looked at is 9. Okay. Any questions about that process?
Yep.
Okay.
I just try to scroll up on your Excel sheet, so there's that.
Uh,
No, like on my mouse, I was gonna. I wonder what I forgot, and then I tried to.
right. I know the feeling. I've done that many times. All right. Let's take a look at the code for binary search. And I think I'm just going to type it right here in Excel. See how that goes. But so I'm going to, and I'm just to keep things simple, I think I'm going to just return -1 if the thing we're looking for is not found. Okay. And just for fun, I think we'll do this recursively. Okay, so we're going to need to know the array. And we're going to need to know low. Okay, so base case. What's the situation where we can just stop right now because we're done? I'll give you a hint. I'm going to actually mid. Okay, so base case. And you don't have to tell me in code, just tell me and just describe it. Right, no
the number
ideas?
at mid is what we're searching for.
Exactly, yes. When target equals mid, that's conceptually that's correct. So I'm going to say if if target submid. Then I found what I was looking for, and I'm going to just return the data at that location in the array. So submit. Okay. You have to use your imagination a little bit here. It's kind of, I mean, because we're just dealing with a simple array of integers, returning array submit seems kind of useless, right? Because we're just returning the target. Oh, that reminds me, you actually need to have a parameter for the target. But, so you sort of have to imagine that, you know, these are objects with a bunch of data in them, and we're just looking for the target is like an ID number or something like that. And then we would just return the entire object.
Wouldn't we want the index normally rather than the thing itself?
No, not necessarily. It depends. Yeah, it could go either way. We're going to go with returning the actual data.
Okay.
I'm just kind of thinking, you know, for example, if this was a member function of a container class, returning the index wouldn't really do the client any good, right? The client just wants the data. Kind of what I'm
Right.
thinking. But let me add. Okay, so that's the base case. I'm going to tell you that there's going to be another base case, but we're going to get to it later. So now our recursive case is going to be if the target comes before array submit, right? Then what we're going to do is we are going to search. Low is going to be the same, but high is going to, in the place of high, we're going to put mid minus 1. Any questions about that? I kind of, I didn't explain that in great detail, but that's basically, I think, matches up with what we did when I traced through the algorithm. But let me know if I need to explain that some more. And finally, the final recursive case will be that target was greater than array submitted. So we'll return binary search low plus 1. I'm sorry, mid plus 5. Yes, that's exactly what the second base case is going to be. And the target is, when it turns out that the target is not in the, okay. Okay, so yeah, this actually is a working binary search function. I mean, well, I guess I shouldn't say that since I haven't compiled it and run it to test it. But as far as I know, that is a working binary search function that works as long as the item's actually there in the array. If it turns out that the item's not in the array, this is going to end up with a infinite recursion, or eventually maybe a array index out of bounds, right? Maybe mid will go out of bounds. I'm not sure, but it's not going to work if the item's not there, right? So how can we check to see? How can we add a base case that checks that? If what? How can we tell that the item is not there? lowest greater than high. That make sense? So what happens is
yeah.
high is here's my finger. High. Does this look like it's on the right view? Yes. Okay. High's over here, lows over here. We keep moving them closer and closer together, right? Eventually, they're going to be equal. And then if the target isn't there, well, if the target isn't there, then we're going to be either increasing low or decreasing high, and they will cross. Okay? So we're going to say if low is greater than high, we're done. And I'm just going to say return -1. That being the signal to the caller that the item was not found. And then we need to change this to all right. Does that make sense to everyone?
Yeah.
Well, I'd have to think about that. I think this is a safer because I'd have to think about whether it's possible that they would just pass each other without ever being equal. And I guess I wouldn't say that an extra call of the function. I mean, if you were really concerned about avoiding one final call of the function, you might be right. But typically that's not going to be a strong enough issue to make me change my code. Okay, so losing my train of thought here. Let's talk about big O for binary search. Okay, so basically what we're doing here is, this is going to be a little algebra problem. We're trying to find an equation that tells us how many elements in the array we're going to have to examine. Worst case scenario, if there are n items in the array. Okay, the way I'm going to do that is, it'd be nice to be able to see this up here. I guess I'll do it over here. Let's make a little table. I don't know if you remember this from algebra, but we have, x and y, and we put in some examples that we know of. So, for example, so this is num items, and this is num number of operations. Sorry, excuse me. Okay. Okay, so if there's one item in the list, what's the worst case scenario? How many items we're going to have to look at? Oh, yes, the answer is no. Okay. Let's bump that up to 3. If there's 3 items in the list, what's the worst case scenario? How many items we're going to have to look at? Okay, we've got 3 items. We're going to look at the first one, or we're going to look at the middle one, and then we're going to decide whether the target is bigger than that one or smaller than that one. And depending on whether it's bigger or smaller, we're going to look at either this one or this one, right? But the worst case scenario is we're going to look at 2.
Yeah, so 2. Yeah.
Right. Okay. Let's try 7. Okay. Bonus points if you don't tell me this. I'm just not serious. But bonus points if you understand why I'm choosing 7. Okay. If we've got 7 items, we're going to look at the middle one, decide whether the target is bigger than that middle one or smaller than the middle one. And then that's going to leave us with 3 items to look at, right?
So 3?
So 3 is correct, yeah. Because we already know that if there's 3 items, that takes us 2 comparisons. So if there's 7 items, that just means we have to do 1 more comparison than we did when there were 3, right? That makes sense? Because
Mm-hmm.
once we do 1 comparison, that narrows it down to 3 items, okay? Can you guess what number I'm going to put next here?
11?
Good guess.
13.
No.
Was a good guess.
Yes. Okay, so if I had, well, I'm going to put 15.
Ah,
Because if I look at the center number out of 15,
At least 7 on both.
then there's going to be 7 on both sides, right? So I know this is going to be 4, right? Does it make sense why I put 4 there without having to think about it very hard?
yes.
All right. Okay. So you see,
You do 31 next.
yes, the next one would be 31. Does anybody see?
It's 2 plus 1, 2 times plus 1.
Times 2
2
plus
and plus
2 to
1
the n
yeah.
minus 1.
times.
To the n or 2 times
to the-
n?
2n
Well,
plus 1.
2
Someone,
to
I think.
the n minus
Let
1.
me get a word in edgewise. I appreciate
Sorry.
that. No. I absolutely appreciate the participation. But somebody was answering the question of how you get the next number in the sequence, right? 2n plus 1 would be how you get the next number in the sequence. But how you get from y to x is 2 to the n minus 1, right? That may be, that's maybe not as obvious, right? But now once you see it, it's like, oh, right. So we could say, okay, if y is 10, what's x? You guys must know what 2 to the 10 is. Okay, I just put that in for fun. We don't really need it, but 2 to the 10 is something you should know. Okay, it's going to make your life in computer science much easier if you just remember that one fact.
2 to the 10 being 1023?
1024.
1024.
Yeah.
Your cursor's over.
Okay, so what we have discovered is that if this is y, this is 2 to the y, right? But that's not what we were looking for. What we were looking for is, how do I get from x to y, right? So if going from y to x is exponent 2 to the y, how do I go the opposite direction? And what's that called? So it's called, so that I'm looking for the inverse, right? What's the inverse of exponent? And the inverse of exponent is log. That's correct. Okay. So I know you all love logs from math, and you're very excited that we're going to be talking about logs now. Let me just say that 90-something% of the time in computer science, when we're talking about logs, you don't have to go deep, okay? But you absolutely are going to have to understand it at this very basic level, okay? If you can understand that the way to get from x to y here is log base, I don't know how to put base, log base 2 of x plus 1. I messed something up here because 2 to the 1 is 2. Oh, that's right. Okay, x plus 1. Log base 2 of x plus 1. Because if, wait, so the equation is, sorry, I'm talking to myself. The equation is y equals log base 2 of, oh yeah, that should be y. Wait, y, no, y, log base 2 of x plus, that's the equation, right? So if you've got y equals log base 2 of x plus 1, that's just another way of saying 2 to the y is x plus 1. And that's what we have here, right? 2 to the y is x plus 1. This is just another way of saying that with the inverse function. Y equals log base 2 of x plus 1. Okay? Even if that's a little fuzzy, you're probably still okay, as long as you get the sense that whenever you divide something in 2, every time you do it, that's going to be a logarithmic algorithm. That's the bottom line that you really have to be comfortable with. And we'll see a couple more of those before we're done here. So, command 1, alt B. Okay. I'm not going to have to type it that often, so I'll probably just stick with this and hope you guys get it. All right, so bottom line out of all of this is that binary search is big O. And so the other thing is that just like when I said the linear search was big O of n, even though really it was more like n divided by 2, but we don't care about the 2. Same thing here. We don't care about the log base whatever. It doesn't matter. All we care about is that it's logarithmic. Okay, so I'm just going to say big O log n. Okay? Again, with the big O, all we're looking for is we want to know the family of functions that the algorithm belongs to. All right, any questions about any of that stuff? All right, fun stuff. I will say that the approach that I'm taking to the big O notation here is very informal, right? I'm not being very mathematically formal about it. In the textbook, you will see a couple of pages where he actually gives the formal definition of big O. I'm not worried about that. I'm not going to hold you responsible for that formal definition of big O. You will study that in Math 4 for sure. For sure. Well, I guess I shouldn't say for sure. I don't know for sure, but you should study that in Math 4. And that's where you can actually apply the formal definition and stuff. Okay. It seems like there was something else I was going to say before moving on, but I can't remember it. So, oh, okay, yes. I want to talk a little bit about whether, so the fact that linear search is big O n, binary search is big O log n. Is that a big win? Switching to binary search, is that a big win or is that a little win?
Given that you have to have assorted data, I'm not sure that it's that big a win. But
Okay, well, I guess I should say then, assuming that the data is sorted. Let me answer Mark's question. You're sort of on the right track there, but it's actually more like limits in calculus than it is like infinity, right? You're working on, sometimes this is called the asymptotic running time. Yeah. Yes. Okay, sorry, I'm playing around with my Zoom windows here. Okay, So I want to actually just talk about for a minute the difference that it's going to make. So let's say we have an array with 1 million items in it. How many operations are we going to have if we use a big O of n algorithm, whether it's linear search or something else? That's easy. Another one, right? Everyone understand what's going on there? That's what big O of n means. What if, so I guess this should have said number of operations for, oops, big O of n. What if we use a big O of log algorithm? And we'll assume that we're talking about log base 2 here. Anybody know, or anybody know how to plug that on your calculator and find out? What is it we need to do? Well, you need to find log base 2 of 1 million, right? Base 2, yeah. Now, actually, I'm going to say by the time we're done here today, you should be able to do this in your head easily, okay? But I haven't talked about that yet, so I'll let you use your calculator. Everybody got a calculator that can do base 2 log? Or know how to, or remember the rules about logs so you can, what? I don't remember. I wouldn't be able to do that without looking it up. But anyway, okay. If someone did that on your calculator, you would come out with something like 19 point something, and I'm going to say, let's call that 20. Okay? Seem like a big win or a little win? To me, it looks like a pretty big win. And that's just 1 million. That's not a huge array, right? What if we've got, an array with 1 billion items in it? Not unheard of, right? So if we use a linear search, that's going to be 1 billion operations, right? If we use a binary search, that's going to be worst case scenario, 30 operations, right? So we're getting into so I guess part of the reason that I'm going into this at such length is, I almost said beating this to death, but is to explain what it is we're doing with Big O, right? When we talk about algorithms that have a different Big O analysis, we're talking about algorithms that have a really huge difference in their efficiency. That's sort of the bottom line point. Mark, I just noticed that your hand is up. Is that just left over from something a while ago? I assume. I'll assume that unless you tell me otherwise. Okay. I want to talk a little bit about how to do this math in your head, just because you're going to be happy that you know how to do it, because this is going to come up a lot. So 2 to the 10 is 1,000, right? And so when I was doing this math here to get the 20, I wanted to know 2 to the what is 1 million, right? So if 2 to the 10 is 1,000, 1 million is 1,000 times 1,000. So 1 million is 2 to the 10 times 2 to the 10, which is 2 to the 20, right? And then to go to a billion, to go from 1 million to a billion, you're just multiplying by 1,000 again, right? So multiply 2 to the 20 times 2 to the 10, that's 2 to the 30. Okay? And then, of course, you can guess that if I said there's 1 trillion items, then the worst case scenario would be 40. All right. Yes, exactly. That's a good way of putting it. All right, I think I am done beating the binary search to death, and we're going to move on and talk about selection sort. Raise your hand. Or actually, can you answer yes or no? Answer yes or no whether you already know how selection sort works, or maybe you used to know even.
Is there something for kinda? Can I do yes
Just
and
put,
no?
yeah. Too bad there's not, right? How come no keeps going between 1 and 2? Someone playing? Is that the kinda? Anyway.
That's me. But yeah,
Okay. So, all right. I'll try not to make this too tedious, but I do want to just show you for in your homework, and if I ask this on a quiz. So here's our unsorted array. I'm actually going to take the borders off. Okay. So what I want to do here is I want to draw a picture, a new picture of the array that shows snapshots of the array after each pass through the array. Okay. So the way selection sort works is find the smallest item in the array, swap it with the first item in the array. But let me just say that again slightly more precisely. Find the smallest item in the portion of the array that you're still sorting, or the portion of the array that has not already been sorted. Swap it with the first item in the portion of the array that has not already been sorted. Okay, so right now none of the array has been sorted. So the smallest item is 15. I'm going to swap the 15 and the 82. So 15, 82. Everyone understand what I just did? Anybody want me to do that again? Okay. And then now I'm going to put a box around that to indicate that it has been sorted. So that's the part of, so the part of the array that has not yet been sorted is the stuff that's outside the box. Okay. So let's make a copy of that. Find the smallest remaining item, which is 35. Swap it with the 55. Okay. Make a copy of that. Please tell me if you want me to slow down. I'm assuming that you're getting this, and so I'm just kind of doing it quickly. Smallest item is 38, so swap the 38 and the 92. So actually now I need to put a box around 38. All right, smallest item left now is 43, so swap the 43 and 67. Put a box around 43 because it is now sorted. Smallest item left is 53, so swap the 53 and the 90. Put a box around 53. Smallest item left now is 55, so swap the 55 and the 92. There's actually a reason why I'm continuing to do this, and I think to stop. I want to see the final product. 67 is now the smallest, so swap the 67 and the 82. Uh, 60 is now the smallest, so swap the 60 and the 90. Oops, did I get that? Oh, bummer. I missed the 60. So I'm going to go back and fix it. I know that you all understand how to do this, and so it probably makes no sense that I'm going to actually bother to fix it. But at this point here, I should have swapped the 82 and the 60, not the 67. So 60, 82. And then we can copy that. Oops. Swap the 67 and the 90. Swap the 82 and the 96. You guys think that the videos are more entertaining than watching you do this? So the 90 is the smallest item remaining, so swap the 92 and the 90. And the selection sort has no way of knowing that it's done. You know, the remaining items are already sorted, so we just keep going. Now the 92 is the smallest item. We swap the 92 with itself. And now we're done, right? We don't have to go through the process again when there's only one item left. Okay. Let's talk about any questions. So if I give you a list of numbers, you can sit down and open up Excel and go through the same process. All right, let's talk about big O. How many of these steps are there going to be? How many passes through the array are there going to be? Basically one for each element of the array, right? Each step here, what happens is we get one more item into the sorted list. So the more precise answer would be n minus 1, right? But we're just going to go with n. So we've got n steps here. Okay, to get from one picture of the array to the next picture of the array, how many comparisons do we have to do? 11, yeah. Because we have to, let's see, potentially, yeah, we have to compare the 82 with the 55, and then whatever smallest we compare on down the thing. So yeah, for our purposes, n works, right? Okay, so we're going to say we've got n steps. Each of those n steps requires n operations. So altogether, that makes how many operations? Right? So we call selection sort a quadratic sort, or an n squared sort. And now you know why. So part of the reason that I like having this picture here is that it is really a visual way of seeing the n squared operations, right? Again, and then I guess I should have mentioned, technically the number of comparisons for each pass is on average going to be about n divided by 2, right? Because by the time we're done, we're only looking at 1 or 2 items, not 11. But we don't care about that. We just call it in. All right. N squared, initial instinct, does that seem good or bad or terrible or what? So
Seems pretty slow.
looking back could be better, could be worse. Yes, it could be worse, not much worse. But looking back at our linear search was big O of N, and that got kind of ugly when we had 1 million items, right? So now if we're doing a big O of N squared algorithm, and we have 1 million items in our array, how many operations is that? 1 million times 1 million, right? Which would be 1 trillion. Okay, that's getting to the point where that's not going to be acceptable if you've got 1 million items in your array. The computer's not going to be fast enough, right? We're going to want to find something better. And then if you've got 1 billion items in your array, we don't even want to think about that. Okay, I do want to show you some code. If you took me for 10A or 10B, you've probably seen my selection sort for my lessons, which I kind of like, but
Oh yeah, that's when I first
yeah,
experienced your swap function as well.
the C++ swap.
You were like, "Don't worry about this, just know that it works." I'm like, "Cool."
Yeah, exactly. But I think instead I'm going to show you the version that I use. So I have a file that I will be posting, and maybe it's already posted. I think it's already posted. That has the code for all of these algorithms, or all of the sorting algorithms. So maybe I'll just take a look at that real quick. I wonder if this will translate into Excel. It's not too bad. Give it a bigger, I guess. Okay, so I remember when I first learned about sorting algorithms, it seemed really mysterious to me, and I don't think anyone ever actually showed me the code. I like the whole thing. Let's try that. That doesn't look good. I think we're going to go with this. But this is not all that hard, right? So the code, I like the entire code. All right, I'm curious. I'm going to have to restart this again. Okay. I'm going to leave it like this. We're going to go with it. So let's just look at this. Okay, we've got the for loop going from 0 to num items minus 1. That should look familiar, right? That's how many passes we made through the array. That's how many steps there were. So everything inside here, what it does is it finds the smallest item in the array and then swaps it with the first item in the array, right? And you can sort of substitute in there when I say in the array, I mean in the part of the array that hasn't been sorted yet. This part, you can see that this code here finds this index of the smallest item in the array. right? Sets it equal to I, and it goes through the rest of the items. And if the item is looking at a smaller than the smallest item so far, switches it out, and then just does the swap. Okay. All right. I just remembered that I have a meeting, and I'm going to stop there. So we'll talk about the rest of the sorts on Thursday. We'll see you all later.
Awesome. Thanks, Dave. Thanks,
right.
class.
See ya.